Hey everybody, today we'll be learning about perpendicular volume by cross-section. Perpendicular cross-sections are planes of surface formed by cutting across a solid, perpendicular to its longest axis. Today our goal is to teach you how to solve problems step by step using various methods like 3D representations, graphs, and real-life examples. As students of AP Calculus, we learn so much in class, but oftentimes we wonder, why are we solving all these problems? What do perpendicular cross-sections have to do with our daily life? How can we relate it to fruits? Can you guess? Let's look at some examples to get some background knowledge on the subject before we dive in. Notice how the cross-sections look. They have a horizontal tops and are of equal width. By measuring these, we can determine the volume of the solid. In this video, we will give you some tips to help you further understand this topic. When we are finding an area between the curves y equals f of x and y equals g of x, with f lying above g, for a is less than or equal to x is less than or equal to b, the integral from a to b of f of x minus g of x squared dx integrates the length of the segment from g of x to f of x, meaning that the integral of a length is an area. Intuition suggests we generalize and say the integral of an area gives a volume. Let's make this idea precise. Here are examples of a perpendicular cross-section graph. Note that the volume is perpendicular to the axis, and based on its shape we can determine what it would look like as a solid, knowing that the area of a square is side length squared, s squared. We can plug it into the given function y equals 1 minus x squared for s and apply the volume formula. For this one, its volume equals the integration from -1 to 1 of 1 minus x squared dx. And knowing that the area of an equilateral triangle is √3/2 s squared, we can plug in the given function y equals 1 minus x squared for s and apply the volume formula. Volume equals the integration from -1 to 1 √3/2 of 1 minus x squared dx. Real-life examples. To give you all a better visual of the concept, we will explain using real food. First, let's see what happens when we use an orange. Imagine the orange as a volume graph. Using this knife, I will cut it into discs, and this knife would represent the perpendicular cross-sections in the real graph. These orange discs are what the graph would look like if we pulled apart each section individually. Now, using a watermelon, I'll show you what it would look like if we found perpendicular cross-sections for a graph of a different object. Again, I'll start by cutting it up into discs, and using these, we are able to approximate the volume. It is also important to note that the smaller you cut the pieces, the more accurate your approximation will be because there will be less space in height between the two slices. A mathematician has a paperweight made so that its base is the shape of the region between the x-axis and one arch above the curve, y equals 2 sine x. Each cross-section perpendicular to the x-axis is a semicircle whose diameter runs from the x-axis to the curve. Find the volume of the paperweight. Let's go! Again, it's really important to visualize the problem, so the first thing we do is make a rough sketch of how it would look like, or even use the calculator to solve it. But let's not use calculators yet in this problem. Let's let f of x equal 2 sine x. Then knowing that to find an area of a semicircle is area equals pi r squared over 2. And we also know that the radius equals half the diameter. The endpoints are known to be x equals 0 and x equals pi, because the curve of the graph makes a semicircle. Now we can solve the problem by setting the volume given to the formula. Volume equals 1/2 pi integration from 0 to pi of r squared dr, which equals to volume equals 1/2 pi integrated from 0 to pi of f of x squared over 2 squared dx equals 2.467. Now, here's how we do it on a calculator using Math 9. Here's the steps we took to find the area under the curve.
There's so many ways to visualize the objects of our life with calculus. Everything we have learned throughout this month can seem difficult just by looking at graphs and solving problems. Many people find it easier to learn with visual examples, and I hope this video helped you understand perpendicular cross-sections even more. A quick example. Here we found two simple objects in the house that probably were measured before manufacture. Now you can see many things depend on calculus. Through calculus, scientists, engineers, chemists, and even economists put in practice everything. We hope this can help in your journey through calculus, and thanks for watching.